Okay, we're going to talk a little bit about energy today. One of the things that I said I'm going to talk about in the next class is the fact that we have trying to describe what energy is in the first place. That seems like it would be an easy answer, right? Physicists, scientists, engineers have been studying energy for about 150 years or so. You'd think we'd be able to come up with a pretty good definition of what it is, but we really haven't. In layman's terms, really. Suffice it to say, it's essentially just an accounting measure that we have that we've noticed that when we assign this certain numbers to a system, we find that those numbers, no matter how we mix them around, always wind up the same. And that incredible amount of consistency is extremely important to how we understand how the world and the universe works. So for the most part, we just take a look at energy and we go with functional definitions. And that's really what we're going to do. I'm going to talk more in class looking at it in terms of the way that Richard Feynman, who is probably the most famous American physicist, certainly into the popularization of science in the 50s and 60s, is a Nobel Prize winner. And by the way, the Nobel Prize was recently awarded yesterday, as a matter of fact, to Higgs and somebody else he had worked with, but it's named for the Higgs boson, so we'll go with Higgs. But he won the Nobel Prize yesterday. But anyway, as far as energy is concerned, we're going to talk about the Feynman definition in class tomorrow. Right now, we're just going to kind of jump right in and start talking about work and energy. And there's two aspects that we want to take a look at here initially. We want to come up with a definition of kinetic energy, mathematically and using our words. Using our words, we would say kinetic energy is the energy that we have because of motion. We've talked about that a lot last year. Real simply, so kinetic energy is equal to 1/2 mv squared. We have found through experiment that this is, when we combine it with other forms of energy, this is the number that we assign to an object because of its motion. All right. So now we have its mass, its velocity squared. Notice the velocity squared, that takes away any negatives or anything else like that. This is a scalar. Energy and work are scalars. Okay, there is no vector associated with it, and that comes. That's pretty important when we take a look at a few problems as we go through. So now. Work, on the other hand, okay, work is something, and this is going to be our first time definition, FD cosine theta. Okay, to be a little bit more precise about it, that's the way that we looked at it last year. I'll probably change the D to an X, and you'll see why towards the end of the lecture. So we're going to change this to force times x cosine theta. And now, if you remember, okay, force, that's a vector. X, well, we're looking at the magnitude of x. That's a vector. Cosine theta, we can write work. And this is for a constant force. Work is equal to the dot product of force and displacement. Now, this is again for a constant force. Again, we see that we get a scalar out of this. Now, the reason why we take a look at work here, okay, it's force applied over a given distance, and why that's so important, why we put this together with energy, with kinetic energy, we have found through various experiments that work is equal to a change in kinetic energy. Okay? And I should be a little bit more precise here, say the net work done on a system is equal to the system's change in kinetic energy. Kinetic energy. The the proof for this is not that bad. Let me take a look at it real quickly here. Okay, we know if we're just looking at magnitudes, okay, we have it's really just a reworking of Newton's second law, and there are all sorts of ways that we can rewrite Newton's second law to suit our purposes. If you go on in physics, your junior year, you'll probably take a look at the Lagrangian and the Hamiltonian reformulations of Newton's second law. This is just a different way to look at. Those are much more complicated. This is probably the simplest reworking of Newton's second law that we have. So now, F equals ma. Now we can take this equation, velocity final squared, velocity initial squared, plus 2ax, okay? Rearrange for the acceleration. Acceleration then is final velocity squared minus initial velocity squared divided by 2x. So now we substitute in, force is equal to m over mv final squared minus m the initial squared, all over 2x. Multiply both sides by x, and we get 1/2 mv final squared minus 1/2 mv initial squared. This is the final kinetic energy. This is the initial kinetic energy. This is the work that's involved. Putting in vector form, that gives us work is equal to a change in kinetic energy. Okay, and that's proving what we wanted to from the very beginning. Okay, so now, one of the bigger problems with that, you take a look at something like this. Okay, let's just say that this has a mass of 50 grams. Okay, 0.05 kilograms. Now, I have to apply a force of about 1/2 Newton. Okay, probably about 0.49. I lift this up and I apply 1/2 Newton's worth of force over a distance of, well, about 1 meter now. You say, well, wait a second, its kinetic energy didn't change. I did work, okay, I raised this up. There we go. Raised it up 1 meter. Okay, I applied a force of 1/2 Newton for 1 meter. I should have a definite change in kinetic energy. Well, the key is it's net work. There's something else that's applying a force to this as well. It's also applying about 1/2 Newton of force. Okay, I apply a little bit more at the beginning. This force applies a little bit more at the end. Okay, the gravitational force is also doing work on this. Okay, it's applying a force down, okay, as it goes up. So what that means, the work that I do, work of me, okay, well, when you look at the force here, the force goes up, and the direction of motion, my delta x, well, that also goes up. So if I did F dot x, okay, that's just going to equal the work of v will just equal force times distance. Okay? Because the angle between them, so theta here is equal to 0 degrees. Cosine of 0 degrees is 1. Gravity, work done by gravity, is equal to the force it applies, divided with x. But now, the force that gravity applies is down. This is the force of gravity. This is the force of me. Okay? My delta x, though, is still up. So now, in this case, this is 180 degrees. Now the work done by gravity in this case is equal to negative Fx. So if I look at the net work here, not net work is equal to Fx minus Fx, which equals 0. So my change in kinetic energy also equals 0. I take my half a Newton force, I raise it up. Okay. Yes, I change kinetic energy a little bit at the beginning. Okay, and I decrease it a little bit at the end. Negligible compared to the amount of work that I do. Okay, so I lift it up slowly. Okay, I'm still applying a force. It should be changing its velocity if it was just me, but it's not just me. It's gravity. Okay. Now the work that's done by gravity, okay, we can shorten it down. Now here's the thing. Okay, if I look at the work that's done by gravity, gravity is only going to act down. Okay, and it's a constant force, so we can look at it as F dot x or Fx cosine theta. Well now, here's the thing. If I'm lifting that up in this direction, so I lift it up going across, okay, take it and I lift it up, okay, the force that's done by gravity here, okay, the force of gravity is down. My delta x goes like this. But now, all I'm concerned about is the angle that it makes here. Okay? The angle that I'm making with the angle here that I'm making with force of gravity and delta x. Okay? So now, really all that I get out of this is, again, that distance. Okay? So really, this is going to be my delta x cosine theta. So that's where that comes from. This is all delta x. If I take delta x cosine theta, I get that. Okay? Now, so what I'm pointing out there is we don't care about what happens side to side. I only care about what happens vertically. So the work done by gravity is going to be the object. The force is mg times your change. So that's going to be the work. That is the work that's done by gravity. Now, we also have work that's done by spring force, work that's done by an applied force in general. And then we have work done by general variable force. We're going to hold off on the general variable force because we haven't talked, we really don't know integrals yet. Although I have to introduce a couple basic things here. Okay. Now, work done by a spring force. I've got a mass that's sliding in here. Some initial speed v0. It's going to compress our spring before it comes to a stop. So I'm going to say V final here, or at least the part where it would hit the spring. This would equal 0. So now, it compresses the spring that much. Right. Final down. This is my delta x. But we also know that the force that's applied by the spring is not constant. The force applied by the spring is equal to negative kx. Okay? In other words, the spring is compressed this way. Okay, the negative comes from the fact the spring is compressed this way. That's my delta x. Right? But the force goes this way. So the spring applies its force opposite the direction that it's compressed. If I made a graph of this, force on spring, X, and I graph this. Now, if it were a constant force, it would just go across. If I wanted to work, you know what? It would just be force times x. I'd have a rectangle, and easy to find the area. The work would just be the area. Well, you know what? It also works for when it's not a constant force. The area, okay, the work done by a variable force is equal to the area of a force versus x graph. Okay? So now, this spring force here, this area right here, that is the work that's done by the spring. Okay? So now, this is x. Force on a spring is kx, so this is kx up here. The area of this triangle is 1/2 base times height. 1/2 base is x. So the work done here is equal to 1/2 the base, so it's 1/2 times x times the height, which is kx. So the work here done by the spring is 1/2 kx squared. And technically, you should be careful about that. That's negative. So now the work done by the spring is negative 1/2 kx squared, where x is how far it's compressed. Think about this. If you have this mass coming in and it's coming to rest, okay, it starts off at V0, it ends at 0. The work has to be negative. We get our negative. Okay. Let's take a look at what happens. Now, the great thing about this, I don't care what happens in between. That's one of the beauties of energy. I don't care what happens in between. You're looking at the state. So now, if I want to figure out the how far that spring is compressed, well now, work is equal to a change in kinetic energy. So I have the work done by the spring is 1/2 kx squared, negative 1/2 kx squared, is equal to the change in kinetic energy, which is 1/2, it's the final minus the initial. My final velocity is 0, so that term goes away. Negatives go away here. I have the halves go away, so I have kx squared is equal to mv initial squared. So x is equal to the distance that this is compressed. It's m over k times v initial squared. Square root the whole thing. You can pull the v0 out if you want. That's fine. V0 root m over k. That's as far as the spring is compressed. Now here's a crazy thing. You just did, for those of you in Calc 2, you're good on this, no problems. This is calculus, okay? Just not using any of the fancy tricks that you learn in calculus, okay? Finding the area under a curve, that is the basis of integral calculus, okay? Now, we'll talk a little bit more in class, a little bit more one-on-one on how to deal with integrals and a more general variable force. Okay, so I want to hold off on that. I think that's enough for now, and I will see you guys in class tomorrow.